which we are going to cover today. So let's start with the neural network. So you have as you can see, you have an assignment lab, which you need to submit, and then you also have the neural network walkthrough. So in the class, we basically went over the concept of the perceptron. We talked about that, it's the early definition of neural network. Basically, it started with the concept of perceptron, when the perceptron, basically the way that it works is we can basically assume it like one single neuron that has a basically weighted sum or linear input and some activation function to introduce some sort of like a nonlinearity. And as we go through the basically through the code series of the basically pre-processing the steps that I'm not going to cover as part of the walkthrough, okay, I have a basically an assumption that you're familiar with these concepts. But basically what we do, we have some random data generated, and the data has some specific basically form. We standardize the data to be sure that this data it's basically proper for the training, and it basically helps with the convergence. And in order to create a perceptron, which basically is just one single node, basically one like you can imagine as a neural network with one layer and one single node here. So what we are basically doing, we are using TensorFlow and Keras, and it's a sequential model, and we add one layer here, and that layer is going to be a dense neural network. Dense basically here means the fully connected, as we saw in the class basically. And here number 1 stands for the number of nodes in this layer. So we have just one node, which is again similar to the concept of perceptron. And there's a parameter for activation, and we decide the activation to be sigmoid. And we define the input shape because the input, basically the data that we have has 20 dimensions. So basically we say that the input shape is 20, and we run that so that we have a perceptron model. Now, the next step is that as part of the working with TensorFlow, you want to first compile this basically model that you have built, which here we call the perceptron. So basically you basically say perceptron.compile, and as part of compilation, we need to talk about when I want to train this perceptron model. As we saw also in the class, we have an objective function which you want to optimize for. And so we need to define what's the objective function that we have and what types of optimization we want to use. So for optimization, objective function, we are using binary cross entropy because the data we have, it's a binary classification. And for optimizer, we are using Adam, and we also discussed about Adam in the class, and we will also going to have some optimization lab over the Adam. And then you also need to define a metric. That means when we are basically optimizing this basically a perceptron training, what's the metric that we care for? And here we just put accuracy. Not that accuracy is the best, but for the sake of this lab, we just selected accuracy. And then after that, after your compilation, you basically need to say perceptron.fit, and fit basically it's what it does here is at this point. It will receive the data that you want, and it basically start the training using the data that you are providing. So here we have the X-train scale, which is the input to the model. Y-train is the labels for those inputs. And there is a parameter called epoch. We are saying that we are going to train this for 50 epochs. And we are going to basically divide the data into batches of 32. And also, additionally, when we train the neural networks, we do need validation data. So you could either explicitly pass the validation data, or you could basically use the training data and split the training data into train and validation during the training here. So what we do, we basically saying that to pick 20% of the training data for validation. And variable 0 here just stands for that to do not basically print out. So when you run this, it's basically going to go over for 50 epochs, and we will see the result after that. Pretty quick, because again, just one layer, one node. And now this perceptron history which is carries series of information. We could basically use it for visualization, for example. But here, what we're going to do first is that the model that we have, which is the perceptron, which is trained version of that model. We're going to evaluate it over a test data, basically set of data that the model hasn't seen during the training. And we have the input and we have the label for the basically evaluation. So as the result, this evaluate function returns us the loss and the accuracy basically. So also here we have loss and the accuracy. Those are the two metrics here. So, and this function here is just for visualizing the result that we have. So here basically it tells us that the test accuracy was almost, for example, 90%, and the loss basically test loss is 0.27. This plot here basically helps you to compare the training and validation, basically loss and accuracy. And as we can see, basically there is some accuracy increases to a certain point for both training and validation. And then after that, the model plateaus. That means technically the model that did not learn much after probably epoch 8 or 9. And similarly here, as you can see, the training and validation loss decreases, and beyond certain level, it's kind of like the plateauing. And again, this is just a really simplistic scenario. And here actually the validation loss is lower than the training, which most likely, most of the time, it's not like that. The validation loss is higher than the training. So that's just a simple perceptron. Now, as we talked in the class, that you could basically we stack series of perceptron on top of each other, and we create a neural network. And that's basically also going to help us with the problem like Zohr, that which perceptrons are incapable of solving by themselves. So what we're going to do here is that we basically picked, imagine the same perceptron that we had, which simply was one layer with one node. Now let's stack series of layers on top of each other, and each layer are going to have multiple nodes. So what we're going to do here is that we define a neural network. This neural network has 3 layers, 1, 2, 3. So if you include the input layer, technically this is 4 layer, but so it becomes an input layer, 2 hidden layer, and an output layer. So we don't explicitly pass the input layer because this is a sequential types of modeling. If it was functional, you actually need to explicitly write the input. But the style of coding we select, which is sequential, so you don't need to pass the input layer. All we need to say that what's the input dimension, basically. So we have our first hidden layer, which is again is fully connected, has 64 nodes, activation ReLU, and then we have another fully connected layer, 32 nodes, activation ReLU, and then we have the final layer and the output layer, which just because it's binary classification, will have one basically output, and it's going to be SIG mode because it's again binary classification. If you have just one output, and that becomes a probability, for example, of class 1, probability of class 0 becomes 1 minus whatever value is the class 1. So we don't need to have 2 nodes. And we're going to do the same thing. We're going to compile this basically model, and then after that, we are going to feed training data to this model. So let that run. It's going to be a bit basically slower than the previous run because now the model is larger, for example. So let's see how long it's going to take. And this one also was quick. So now we're going to get the loss and the accuracy, and then we're going to plot that. So the first thing we can compare with the perceptron was that so the test loss, his test accuracy increased, and test loss almost technically test loss is almost the same. And but what we are going to see here is that so if you compare the training and validation, as you can see that the training accuracy is increasing, but validation accuracy after a certain time it's going down, which is a good indication of overfitting. That means your model is doing a really good job in the training, but is actually start to doing reverse, like it start doing bad in the validation. And you can see the same thing in the loss function also, or the loss history, that the training loss is keep going down, but the validation loss start to increasing. So after this point, you have basically overfitting. And this is a good comparison for us to understand that when we did single node, everything was smooth, so that we didn't have much of basically overfitting. But as soon as we add additional nodes, additional layers, the complexity of model increased. And that's why, the neural networks are really basically prone to overfitting. And that's the scenario that here has happened. Okay, so now what we're going to do is that we wanted to, as part of this lab, to also test out this neural network over this MNIST data set. Which MNIST data set, it's a hand written digits basically data set, and we're going to use it for classification. So as you can see, for example, if this fully connected network has 9, basically we will have 10 output nodes, because we're predicting or classifying 10 classes. So at first, again, we just load the data. We do some data pre-processing, which just basically pass from those. The only thing here, additional thing we need to do, is that for the labels, we just convert this to one-hot representation. So if it's, for example, here, as you can see, if the output is 9, so we get a vector of size 10, which the first 9 elements are 0, and the last element, which is corresponding to digit 9, will have a value of 1. Okay, so then here, let's go. So here we're going to basically build the model. So we're going to use sequential. This time we specifically pass the input dimension. Not necessary that you need to do. Actually, you can just pass the input dimension again as part of the dense. We build the model. This is the summary of the model. You're using the dot summary from TensorFlow. You can basically get some visual perspective of your model. So as you can see, this model has 3 layers. So the numbers that actually you see here, dense 5, dense 6. The reason is that I'm running through the same Jupyter. So I previously have created one layer here, one layer. Then I have 2, 3, 4. So I already created 4 dense layer. So here, when I start, it start counting from layer 5, 6, 7. So that's the reason for layer dense 5, just the naming. And it gives you what's the output of each layer, and what's the total number of parameters that you're learning in that layer. At the end, this 3 layers dense model has 109,000 total parameter. They're all trainable. That means all of those will be adjusted, your weight and biases. 0 non-trainable. So what we do is the same thing. We're going to basically compile this model with one difference here, is that because previously we were doing binary classification. Now we are doing basically class classification. So the loss function changes from binary cross entropy to categorical cross entropy, because it's multi-class. So we compile this, and then we let this model to run. This time I let the basically verbose to be 1, so we can see basically what's going on. So we're going to run it for 10 epochs. And as you can see here, it shows the accuracy. When you use verbose, basically verbose, it shows the some output for training and validation. So you will see accuracies for training, loss for training in each epoch, and validation accuracy and validation loss. So we can evaluate that on the test data, and same thing, visualize the result. And as we can see, the accuracy, again, for validation indicates that after certain points, the model has some sort of like overfitting. The overfitting here is not really bad, because so basically the validation loss and accuracy is kind of like a plateauing, so it's not like increasing going upward, but still in compared to the training loss and accuracy, it's we have overfitting, but maybe with some plateauing basically scenario. So this was the walkthrough for the new